start off. She is I'm going to get her title right, but the director of the Navy Technology Center for Safety and Survivability at the Naval Research Lab, and she's an expert, apparently multivariate decision making, but also in testing, and she'll speak about that. And then her collaborator, Abhishek Mataya, who is the CEO and founder of N5 Sensors, will also speak after. So thank you very much.
All right, you said. I've been working in the area of sensors and multivariate data analysis for about 35 years now. And a very important aspect of both of those is testing. And testing is an area that's frequently held off to the end, given very little resources, and overlooked. And yet it's probably one of the most important areas with regard to sensors if you're the person that's going to rely on that sensor in the field. This presentation is funded by the Department of Homeland Security, both the Explosives Division and the First Responders Group. And let's see. So this is an outline of the approach that I'm taking for this presentation. I'm going to talk about test objectives, what we would like to know about the sensors, and then some frequent mistakes that people make. And then I'll describe a test bed that we built for the Department of Homeland Security for explosives detection. Explosives are very sticky compounds. They tend to hang up on things. We had to take a lot of different characteristics into consideration in designing this particular test bed. And it took us a number of years to do that. And then recently we started working on a smaller version of the test bed that we refer to as the TVGen, which stands for Trace Vapor Generator for Explosives and Narcotics. And the reason for this particular instrument is because DHS recognized that manufacturers need the ability to generate these explosives at their facility so that they know how their sensors are working before they pass them off. And so we took some of the lessons we learned from our original test bed and made it into a smaller, more portable device that could be given out to performers. And then finally, I'll make the transition to the next talk and talk about the work that we're going to be doing with N5 sensors. So what types of information do we need to know about sensors? For one thing, we need to know how the sensors are going to operate in the environment that they're intended for. We need their response time, their recovery time, and their sensitivity. And the sensitivity can be either limit of detection, which is usually the minimal amount that you can see above a blank, or limit of quantitation, which is usually quite a bit larger. So limit of detection is usually 3 times the noise, whereas limit of quantitation may be as much as 10 times the standard deviation. And then selectivity. How is this sensor going to work in this open environment? How is it going to behave with potential interferences? How is it going to behave with mixtures? And so one thing that a lot of sponsors will use is the receiver operator characteristics to describe how that sensor is working. And that's looking at false positives versus the detection rate. And if you're on this 50-50 line, well, you might as well have a quarter. But as your sensor technology gets better, this sensor is a little bit better than chance, whereas you really want your sensor response to be up here, similar to this yellow line. And as I mentioned earlier this morning, sensor-to-sensor reproducibility is crucial because of calibration. We can't afford to test and develop algorithms for every individual sensor. Once we develop those algorithms, they need to be able to transfer to the next sensor. So that's one of the things that we will want to evaluate during our testing. Sensor repeatability. If I expose it to a chemical is that chemical going to have an effect on the sensor? Is there going to be hysteresis? Or are we going to get the same response over and over again? And then, of course, relative humidity. Anytime you're working in a real-world environment, relative humidity is always a factor because water is present at so much higher concentration than the analyte that we're typically looking for. And sometimes you have to mitigate this, as I mentioned with the IMS units, and temperature effects is another one, that sometimes you have to incorporate into your package ways to control the temperature if your sensor has a lot of effects. And then finally, dynamic range. So we're not only worried about what the sensitivity of the sensor is, but what happens if you hit it with a high concentration of something? Does the sensor recover? And is it going to be good to you for the next measurement? So frequent mistakes that we've seen people make that are developing sensors: testing it in dry nitrogen rather than in humid air. That's really common. I mean, it's not a bad idea to test in dry nitrogen initially. That might be your first test, but eventually you have to move to the environment that you expect the sensor to work in. And then some of these other parameters that I have on here have to do with the test bed itself. If your vapor generator is not stable, then you don't know what your sensor performance is. So these are things that you have to take into consideration, and this was a big factor, particularly with regard to explosives. The stability of the temperature and relative humidity controls, this is of your test bed. So if you don't have control over the parameters that you're using to test the sensor, then how can you know how the sensor is behaving? Another factor is you don't collect enough data to have statistics so that you know what your limit of detection is or your limit of quantitation. And then carry over from a previous analyte. This can be a problem. One example that we had when I was working in the SAW development many years ago is the packaging had a leak. And it turns out when we switched from clean air to contaminated air, there was a difference in the pressure drop. And that meant that room air was leaking into our sensor package and impacting the sensor response. And we were pulling our hair out for the longest time trying to figure out what was going on with this sensor. And it turns out the packaging was leaking, and it wasn't the sensor at all. It was the package that was testing the sensor. And so we also need to be able to rapidly switch from analyte to clean air if we want to measure these things like response and recovery time. And we need side-by-side testing so that we can better understand how a batch of sensors work or several batches of sensors work against the same concentration. And this gets back to the calibration transfer and the fabrication reproducibility. And so let's move on to how we considered these when we were building the explosives test bed. So the key features, and I'll go into examples of these as we proceed through the talk: vapor generation. It has to be reproducible and stable. You can't test a sensor if you can't trust your vapor generator. And this is true even if you buy a calibrated gas standard. It may be perfect the day it's delivered, but it's going to degrade while it's sitting in your laboratory. And unless you have control over that vapor generator, you don't know how your sensor's performing. Many times when we're dealing with trace, we're worried about mixing different size volumes. So if your analyte you're introducing in the milliliter range, but you're diluting it with liters of air, how do you get that proper mixing so that you know you have a uniform concentration to expose your sensors? Stable delivery, materials compatibility. Many of the chemicals that I've had to deal with over my career, this is crucial. Early days working with hydrazine for NASA. Hydrazine was highly reactive, it stuck to things, and So materials compatibility was crucial. And this is also true for explosives. And this impacts the uniformity of the data that you're going to be collecting. So you even have to think about, well, how are you going to test those sensors? What kind of chamber are we going to make? What's that chamber going to look like? What are the flow dynamics of that chamber going to be? And then finally, validation. Even if you think you can trust your vapor generator and you think everything is stable, you still need to validate at your test bed. What is your sensor being exposed to? And you can do this either by collecting 10x tubes and analyzing it with a GC mass spec or something to that effect. But one of the downsides of doing that is you're collecting over a long period of time, and therefore you're integrating that signal over a long period of time. When we first built the test bed, we were using a vapor generator that had a syringe pump. Well, we hooked it up to one of our sensors that was being developed at NRL, and that sensor was sensitive enough it could see the pulsing of the syringe pump. And we had this oscillation that we finally realized was the same frequency as our vapor generator. Unexpected contaminants. As when I get into this talk, I'll talk to you about our zero air generator. But when we were using the 10x tubes, we're only looking for the analyte that we're looking for. When we added an online capability, we discovered that the zero air generator that we had bought was putting out a plasticizer. And we saw it plain as day in the mass spec data. They had used Tygon tubing next to their catalytic converter, and as time went on, we were getting plasticizers in our air. Well, how's your sensor going to like plasticizers? Maybe not so well. So this is the test bed that we built for DHS. It's a little bit of a monster, but remember, explosives have extremely low vapor pressure and they're very sticky. So it involves a computer so that we can completely automate and standardize the vapor delivery. We can set up protocols that we can run the same over and over again, and we've built multiples of these, and those protocols can be transferred to other laboratories that have the same test bed. We have 6 identical ports so that if we put 6 sensors in line, we know that they're seeing exactly the same vapor at the same time. Our zero air generator is down here, and then our ability to control the temperature and the relative humidity. And then we also have the ability to introduce interferences, and all of this is in an oven so we can control the temperature. And then finally, we usually reserve 1 port to go to our online capability so that we can test in real time the vapor that's coming off the test bed. So the test bed has a dual manifold system, and what we used was stainless steel that we then had treated with a silk inert coating by Restec. And this allows the stainless steel to be more inert to the explosives, and we've demonstrated in our laboratory the extreme difference between trying to pass TNT or RDX through a piece of stainless steel tube versus one that's been coated with silk inert. We use 2 different manifolds so that one is always dedicated clean line and the other one has our analyte in it, and then we use solenoid valves to switch back and forth between the 2 so that we can measure that response time. Our input allows us to introduce multiple different analytes, so we can do 1 or several and create mixtures. And then finally, we have a custom mixer, that's a vortex mixer, that allows us to mix those very small volumes with large volumes and make sure that we get uniform distribution across all 6 of the sample ports. The conditioned air is important. In the laboratory, we can use house air and clean it up. But if you're not in that type of laboratory, you need something else. And we chose this Environics zero air generator. And these are the specifications that were provided with the device. We've been using these in our laboratory now for 7 years, and they work quite nicely, with the exception that it produced a plasticizer. After we were able to identify where the plasticizer was coming from, we corrected that and then tested to make sure that it wasn't happening. Then we went back to Environics, and they have since corrected it in their device, I believe. The Miller-Nelson is a device that allows you to control the temperature and the relative humidity of the air, and that's a very handy device to have for this type of testing. So for test vapors, the test bed allows us to introduce test vapors from a variety of sources. Some gases you can purchase using calibrated gas standards, but again, I suggest that you validate these and make sure that what you got is actually what you ordered is what you got. And these do change with time, so pay attention to that. We also use the Kentech that has permeation tubes in it, and these permeation tubes, there are 500 different ones available with a variety of different types of chemicals, plus you can order custom ones or you can make up your own. And then finally, for the explosives, we created our own custom vapor generator, which is a pneumatically modulated liquid delivery system. So what we do is dissolve the explosive in water, because we're doing this in humid air anyway. So it's present at a very small, low amount. And then we spray that using a nebulizer into this heated tube and vaporize it onto our test bed. And this allows us to get parts per quadrillion levels of the explosives in a very uniform way into the test bed without seeing pulsing from a syringe drive. That's why we use the pneumatically modulated. So this is an example of the types of reproducibility that we were able to achieve. This is all 6 ports, and this is for TNT at 1 part per billion, 200 parts per trillion, and 50 parts per trillion. And you can see that it's very uniform across all 6 ports. And also the test bed provides a dynamic range of vapors that is reproducible and available for testing a variety of different types of sensors. And then finally, the online verification system. We purchased a commercially available instrument from Agilent that uses, has a mass spectral detector with both electron impact as well as chemical ionization, as well as an ECD detector, and it has a Gerstel online cooled inlet that allows us to collect and then desorb into the GC mass spec very rapidly for validating in near real time. We have a new point every 4 minutes, and this is an example of one of the responses that we got for RDX. And you can see the baseline here, and then when we turn the valve, the response. And so it's very nice to know when you have a sensor hooked up that you know you're generating the vapor at the level you expected to generate it. Well, one of the reasons DHS wanted to put this test bed at the Naval Research Laboratory is we're a research lab, and they had people like professors that were developing sensors and materials that they thought would be applicable for explosives. And they don't necessarily come to us with an instrument. They come to us with a sensor or a material. So we needed a way of testing these materials in a very uniform way. And so we decided to use these ZIF sockets, and we pre-programmed in our data acquisition software every single pin, and we can tell the person, just bring us this format and just tell us what are the in pins and the out pins, and we can very quickly put it together. We have electronic chambers that allow the explosive vapor to come in. This is all heated, and we do it in this impactor design so that the walls have little interaction before it actually gets to the sensor. And we also have a chamber for optical detection of devices, because some of the people that brought us materials that either had chemiluminescence or fluorescence, and we use the same impactor design that we used on the electronic one, but we're then measuring the optical of their various sensors. So these are the types of things that one has to take into consideration when testing sensors. So this is an example of some of the results we've gotten for the explosives that we've tested. These are the saturated vapor pressures, and then using the 10x tubes, this was the type of detection limit we were able to get in a somewhat realistic time. We were sampling for 60 minutes, in this case 30 minutes, and then we could get down to the part per trillion level using 10x tubes. But explosives aren't going to be present in the atmosphere at part per trillion level. So using the online capability and the cryogenic trapping, we're able to get TNT and RDX down into the parts per quadrillion level with a 4-minute sample, and then the more high vapor pressure explosives are in realistic concentrations as well. So the TV Gen is a smaller version of the same thing. We use some of the lessons that we learned about generating vapors, particularly explosive vapors. We use the pneumatic vapor generator to deliver not only the explosive vapor but also the relative humidity. Again, we use the dual manifolds, and we were able to switch back and forth, but we provide a single port. And again, all this is under computer control to provide a uniform explosives or narcotics vapor. This is the inside of the instrument. This was built in-house at the Naval Research Laboratory, and we use, because of the high temperatures that we have to achieve for explosives to keep it off the walls of the manifolds, we use this timing belt to switch the valves back and forth between the clean air and the contaminated air manifold. And this is an example of some of the data that we've received off of the TV Gen. This is over several minutes. You can see the stability of TNT at the part per quadrillion level, and then RDX with our RSDs are pretty good. And the idea behind this TV Gen is that we can now put this in the hands of the performers so they can do some of the testing in their own site before they go to NRL or TSL for verification of their sensors. Another thing that people should consider when they're testing sensors is the environment that they're going to be functioning in. We've recently created a facility at the Naval Research Laboratory called the Laboratory for Autonomous Systems Research, and in this facility we have several different types of environments. What we wanted to do was, rather than just going straight from the laboratory to the field, is to have a transitional facility where we had control over the testing, but we could introduce some of the variabilities that you would find in the field. So in our sensor lab, we have one of the test beds there for doing vapor generation. We also have a walk-in environmental chamber, which is here. This is a 10-foot by 15-foot chamber. And right now, as we speak, I have testing going on there for explosive sensors, with people doing the testing inside the chamber, both at freezing temperatures -20 and also at 48 degrees C to test the extremes of the instrument in this condition. We also have a smaller environmental chamber that allows us to do not only temperature and relative humidity, but also altitude. And we have an aerosol lab that's essentially a wind tunnel so that we can introduce real world type contaminants into our air streams. We also have several environmental rooms. There's a desert room complete with sunlight, heat, sand, wind, and a rock climbing wall for people that are looking for something to do in lunchtime. And we can put in different types of sand depending on the type of sand that we want from around the world, and create kind of a mini environment to test the sensors that might have to work in a desert environment. We also have a tropical rainforest. The tropical rainforest is quite nice, has a beautiful stream running through and beautiful plants, and we actually had bananas from our first harvest shortly afterwards. So these are things where you can test your sensors in a realistic environment, but still have control over things. And then finally, we are being funded by DHS First Responders Group to evaluate the N5 sensors, and you'll be hearing from N5 shortly. And the types of testing that we're going to be doing is looking at characterizing the sensor responses, and this will be done initially just at one concentration at one relative humidity in air. And then we'll make things a little bit more complicated by varying the concentrations that the sensors are expected to work at. And then we'll make things even more complicated by varying the humidity and the interferences as well as the concentrations. And this will all be done for a number of gases that are of importance to first responders. And some of the considerations that we have to take into consideration when we're doing this type of testing, particularly of such small nano devices, is how do you want to do the sampling? Are these devices going to be passive? Are they active? Are we using a fan? Do we have to consider phase velocity, because nothing's really static? And what's the optimal flow rate? What's the dwell time needed for the interaction with the nanoparticles? And what is the expected operational conditions that this sensor is going to have to operate in? And so we try to gear our sampling to meet those characteristics. So with that, I'm going to switch gears with N5 sensors.
So, very nice presentation. Thank you. The biggest one is the humidity, but also the VOC in the air. That's a big problem, and that usually affects the baseline. So, and not only affects the reading, like what you just mentioned, the humidity, but also the baseline actually changes. How do you get rid of that? I mean, the only way, I work with this different field, and the only way I can get pure air, no organics whatsoever, it's not to use charcoal filters, but actually to use bubbled up nitrogen, bubbled up oxygen, mix them together. And that's how you get completely pure air with no organics. So how do you go back to the same baseline, and then how do you distinguish the effect of the organics and the effect of the humidity when you actually doing the reading?
So that's one of the reasons why we're doing a dual manifold, so that we can switch back and forth and we can slowly add up the analyte that we're exposing the sensor to. As far as cleaning up the house, so when we clean up lab air, we run it through first a oil separator, and then we run it through multiple filters, and including Purafil to get rid of the NOx, because we sit next to 295, so we have the pollution from the cars going by. And that is a very zero air. And it even scrubs out the CO2, which for some sensors can be a problem, and sometimes we have to add back in the CO2. The zero air generator that we used here met the requirements for DHS, and that's good for this type of environment, but we typically do clean up the lab air very extensively initially when we're doing sensor development.